Hello everyone, and welcome to this session about smart battery functionalization. And it will be a great pleasure to guide you through this session, which is 1 hour, and I'm the moderator. I'm Kristina Edström, Professor of Inorganic Chemistry at Uppsala University. I'm also the coordinator for Battery 2030 Plus. So welcome everyone, and welcome everyone that will participate today. I think on the next slide, we will see the agenda for this session. So please put up the next slide. Oh, that went quickly. We will first have a little bit of a lecture on smart functionalities, why and how. And based on that, we will have a panel discussion showing a little bit of examples from the sensoring field. And after that, some example from self-healing smart functionalities. And then we will have a panel discussion followed by Q&A at the end. And I will very soon present all the actors for you. But I would like to present our lecturer for today for this session. So next slide. Here he is. Smart functionalities, why and how. And this is Dr. Alexis Grimaud from Collège de France in Paris. And I don't know anyone who could be better than giving this overview for us than you are, Alexis. It's great that you are here. Thank you so much. And welcome to deliver your presentation.
Okay. Thank you, Christina, for this really nice introduction. I'm not quite sure if what you say is right, but in any case, I would like to thank you for inviting me, and I will try to just give you briefly the why and how for smart functionalities. So indeed, when you look at what's ahead regarding the research challenges for the battery field, there's obviously a lot which is being done for developing novel chemistries, and we've actually seen that yesterday during a session. Some of those chemistries are short-term goal, like sodium-ion, solid state. Some can actually be much more long-term goal. But if you go to the next slide, in addition to those researches developing to design novel chemistries, you could actually think about enhancing the performances and actually developing further the current battery technologies by adding functionalities to them. So if you look at what we currently have and the way it's currently structured, for instance, when you integrate a battery in an electrical vehicle, you obviously have connection and some communication between the BMS and the battery module and pack for the charging as well as for the train and the motor. So obviously what it does, it's driving the way you charge and discharge your cell. But if you look at what's going on inside your cell, and especially the chemistry, we know that there are actually many different issues that are actually going on. And what's currently missing is this feedback loop from the chemistry inside the cell back to the device, so back to the electrical vehicle. And what we believe that if you provide more functionalities, you could actually, first of all, push further the performances of those batteries, because you can actually push the operating conditions. You could also extend the lifetime of those batteries, as well as most probably give a second life to those batteries and actually improve the way we recycle them. So if you go to the next slide. So obviously, if you look at all the major degradation mechanisms that we have within a battery, they are actually well characterized. We know by postmortem or ex situ analysis what they are and what they actually triggers inside the cell. So it can be actually mechanical issues, so just cracks or mechanical constraint related to the cycling of your electrode. It can also be much more chemical, such as dendrite formation, as well as the release of species in the electrolytes and the reactivity of the electrolytes with the electrode to form the SEI and the passivation of the electrode. And the question that's well, we know that postmortem and ex situ, but the question is, how can you actually anticipate and cure all those dysfunction. And to do that, well, the first step will actually be to be able to sense those degradation during the battery running. So during the operation of the battery, you actually want to be able to sense and localize those issues. And this is where actually sensing come into place. Once you know and you sense those issues, you can actually trigger what we call, and that's I will actually briefly introduce that, what we call self-healing. So you trigger either a mechanical or chemical function that will actually repair your batteries and enhance the lifetime and allows your battery to run much longer. So if you go to the next slide. So regarding sensing, what we probably want to say first is that sensing in the battery field is actually not novel. And for instance, it actually began with the lead acid batteries. And there, I won't go into all the sensing capabilities and what has been developed, but the idea behind that is that in lead acid batteries, the liquid electrolytes participate to the reaction, and you can actually sense the physical properties of the liquid electrolyte and actually correlate that with the state of charge of your battery. So very early on, researchers actually realized that sensing capabilities in lead acid was actually a very good way actually to keep track of the state of charge. So if you move to the next slide. Obviously, there are many different types of sensing, and actually that's really nice because the next presentation will actually cover that in greater details. But you can actually separate them into three main categories. It can be electrochemical sensing. It can also be acoustic sensing or optical sensing. So you can actually introduce all those different functions inside the battery and actually monitor all the degradation issues that I've been talking about before. So either issues related to thermal runaway, related to crack, dendrite, related to chemical species related actually released in the electrolyte. What we have to admit that each sensing capabilities has its own pros and cons. So it will actually be good for one thing and may actually struggle for another one. And the main idea is right now is how we can actually couple them and coverage all the events that we have inside the battery. As well as what the field is trying to push for is, since we will actually generate a lot of data when during the acquisition of all those sensors, there's a lot to actually be done regarding to data management and signal processing. As well as when you talk about introducing a new functionality in a battery, eventually it always goes down to this question of what is the manufacturing cost of introducing this new function versus the benefits that you have in terms of lifetime and in terms of performances. And so if you go to the next slide, so the idea is that if you sense those dysfunctions, so if you are capable of understanding them and localize them, then you will actually be able to trigger this type of self-healing functions. So the idea there is that you could actually repair the battery, and you could do that at different locations. It could be either in the binder itself, so the binder that actually holds the active material all together on the current collector, with some dynamic interaction of this binder, providing elasticity to avoid cracks. And you could also think about self-healing polymers, electrolytes to actually suppress dendrites, or you could also think about introducing some scavenging agents inside the separator or inside the electrolyte, or even inside the binder to actually suppress the parasitic species. Then the question is like when you talk about self-healing, it could be autonomous, so we'll actually self-repair by itself, so that will actually be triggered by intrinsic repairing function, or it could be non-autonomous, which means that it will actually respond to a stimulus that you will generate when you would actually have sense that there is an issue going on inside the cell. So if you go to the next slide, so overall, the overall idea behind that will actually be, okay, we have a cell. So click on next, maybe show everything. That's going to be much easier. Okay, the next one, I think there's one. Okay, there. So the idea, you will have actually a lab on the cell where you can actually sense all the different properties that you want to understand inside your cell. Once you have that, you can actually pass the information to your battery management system. And there, that's what I just said, there will be a lot of data generated. And this is where most probably, and we know that we are trying to push for that, there will be a lot of interaction with AI, as well as with numerical twins of batteries. And once we can actually gather those information and understand them through the use of AI, we can actually trigger actuators for self-repairing the batteries. And eventually what you do when you do that is actually, you can actually provide this kind of electronic passports, which is also something that we've heard about this morning, where you can actually enhance and you can provide a better durability, safety, as well as increase the lifetime. What you will do is that you will actually start to predict what's going on in your battery. And overall, the idea is that you will actually go towards much more efficient usage of your battery. And so I think you can go to the next slide. From that, there was a very brief introduction, and I'm actually really glad that this introduction will be followed by actually a really nice talk where we will hear more in details about what is done in those topics. So thanks a lot for your
Thank you. Thanks a lot, Alexis. We have actually a question for you before you leave us, and that is, could you add more about meaning of intrinsic repairing? Could you say a little bit more about intrinsic repairing, please?
Yeah, so I guess some people talking after that will may discuss that. Indeed, you can actually have some function, and this is something, for instance, for polymer. Self-repairing of polymers is something that has already been done. You can actually integrate functions through hydrogen bonding or through other functions where actually the chains of your polymer will actually regain their initial functions if you actually if you start to have some elongation of your polymer and so on and so forth. So you can have some chemical functions that will actually re-interact with each other after a mechanical issue.
Thank you. And the last question for you. What kind of actuators for self-repair are possible? Have you any ideas or suggestions?
Yes, this is where, for instance, temperature could work very well. Some function can actually be triggered by temperature. I didn't cover that, but if you make the parallel with what we do in medicine, where indeed you can actually release drug upon external stimulus, you could actually envision like encapsulation of some chemical functions, where you would actually break the encapsulation with like some thermal actuators. So anything physical, thermal, will actually work pretty well. But could be other things that we can actually think about.
Thank you so very much, Alexis, and you get a thanks also in the chat function for answering these questions. So thank you.
Thanks a lot.
So now we are moving on to more discuss sensing capabilities and self-healing capabilities in more detail. And we have a little bit of an issue because we know we started off yesterday with 3 speakers from 3 of the Battery 2030 Plus projects. Those of you who don't know Battery 2030 Plus, it's a large-scale research initiative with a roadmap. And in this roadmap, we have defined the challenges to accelerate the discovery of new materials and concepts. We also seen smart functionalities as one tool, but also a challenge to actually improve the batteries of the future. So this roadmap is implemented now in a number of projects, and we have 3 sensor projects. And unfortunately, Henning Lorman from the Spartacus had to resign yesterday evening late and couldn't find a replacement. And we also learned this morning a very, very unfortunate accident for Martin Luco in his family. So we are stuck here with Olivier, but we are also lucky because we have 2 more speakers. We have Maitane Brecher and Maria Wilkman, who will talk about self-healing. And for the Spartacus Henning Lorman project, Maitane will help me. So you will now hear presentations for all the 3 projects, but you have to bear with me when I'm giving the one for Sensibat and the one for Spartacus. But we start with Olivier Racour. I'm very happy you are here, and you are working at CA in France. So I leave the floor to you. Thank you.
Thank you, Christina, for this introduction, and thank you for the invitation to talk today about the project Instabat. It is a project that was started around 1 year in the framework of batteries 2030 plus umbrella, and it is a European project. The objective of this project is to develop a proof of concept of smart sensing technology and functionality integrated into the battery cells. As we present just before Alexis, the idea is to put inside the cells many type of sensors to have a better view of what's happened in the sensor in the cells, sorry, and to analyze the data and extract the information to improve the function of the BMS and the SOX indicator. This project is there is many partners in Europe involved in this project. You can see here the partners. There is this project coordinated by the CEA, but we are also CNRS inside Lyon, University of Aveiro, Varta Microtechnology, Faurecia, and Infineon. Okay, next slide, please. Yes, in this synoptics, I just show you the goals of the project and how we, what is the way to go to a solution. In this project, we developed 2 kinds of sensors. The first kind of sensor is a virtual sensors based on the multiphysics model of the cells. These models are very useful to simulate the degradation phenomenon on the performance of the cell. We use Newman models, but it's very big models, and it's hard to use this in real time. And to have virtual sensors, we need to reduce this model in the most simply way. And in the project, we will to develop 2 kinds of virtual sensors. Virtual sensor for emulate the temperatures and also the electrochemistry property called T-base and E-base. These virtual sensors work in real time with as input the physical measurement at, for example, 1 point, and it can be extrapolated the property in all the volume of the cells. In other way, we develop 4 kinds of physical sensors based on optical fibers. We have 2 kinds of sensors to measure the temperature on the lithium ion concentration, but also the strain on the batteries based on the luminescence and FBG. We also develop a reference electrodes and photoacoustic sensors. The reference electrode is to measure the potential of the cells, and the photoacoustic is to measure the production of gases, especially for CO2. In the project, we don't develop only the sensor, we also develop the integration of sensor into the cells, and we work on the raw measurements, the pre-processing data, the algorithm associated to extract the information, and the definition of SOX and the interaction with the battery management system. And the objective of all this work is to improve the lifetime, the safety of the cells, and also the second life, because if we know the history of the cell, we can determine a better way to reuse this battery, and of course about the recycling. And we studied 2 particular cases. The first case is a height and low temperature condition, and also the fast charging. Next slide, please. Yes, I would like just to show you briefly 2 success stories. First, it's about the virtual sensor. We have developed the the models of the cells, because we work on the cells and real cells with material provided by Varta, and we work on the last generation of the cells. And these P2T models work well and will be validated by compared to the experimental data. And from this base, we have developed a P3D model to have access to the electrochemistry inside the cells, the thermal behavior on the cells. And we can simulate, for example, you can show here in this slide, the thermal gradient inside the cells during the cycling condition with a very good accuracy to the experiment. And the next step, as we showed just before, so it's to develop a model, a reduction of this model to develop the E-base and the T-base sensor, the virtual sensor. Next slide, please. Regarding to the physical sensor, I just want to show you an example about luminescence sensors and to explain in more detail what we do. To measure the temperature by optical luminescence, we use some materials that have property, luminescence properties change with the temperature. The first step is to identify the optical probe. To do that, we have testing and synthesis different kind of luminescence material, and we're testing the luminescence property and also the variation of this property regarding to the variation of the temperature. Then, when we have find the right probe, we put this probe into the fiber. You can show in the middle of the slide an example of deposition of this probe at the end of the optical fiber, and we can test also the optical variation of this probe against the temperatures. And we show here in the thermal characterization, there is a good linearity between the variation of the optical signal to the temperature. Now we have the optical sensors for the temperature, and we can put it into the cells. You can show in the first part. We are testing the integration of this optical fiber in the cell, and it's a challenge because the cells must be working with the sensor inside, and there is some critical issue to have the integrity of the cells, but it's work, and we can show here the first result with the variation of the response, optical response of the optical sensor during the cycling condition, and also the thermal characterization associated. In this case, we have testing this sensor in up to 2C. And the success is we have proved that the development of optical fibers luminescence sensors as a thermal probe. We have also performed the calibration of the sensor. We have validated that the cell integration, and we detect the thermal variation. The next step is to increase the sensitivity. We also perform actually stability test and aging test on this sensor, and also we are under the preparation of different kind of cells with this sensor inside, and there is two steps. The first is working on cell aging and to analyze the degradation phenomenon by post-mortem analysis to correlate the response from the sensor to the degradation mechanism. Next slide, please. I think it's all. Thank you for your attention, and of course, if you have any question.
Thank you so much, Olivier. There is actually one question. Which software are you using for the electrochemical simulation of your battery cell?
Yes, it is. We use console as tool to simulate the cells, because we use DFN models for this one.
Get a thumb up for this. That's good.
Thank you.
Okay, I suggest that we move on, and Next presentation is about the SensiBat project, which is cell-integrated sensing functionalities for smart battery systems. We improved performance and safety. Are there any of you in the audience that belong to the SensiBat project? I ask you to forgive me for my very tough, very hand-waving overview. I'm also asking my colleagues in the group here, because we have joint meetings between the different projects every second week, that you can help me with this. But the overview of this project is that we have the sensors that are to develop are to probe pressure, temperature, impedance. So in this case, the project is actually developing the sensors and different sensors for different things. And then, of course, it's a question how you integrate this in the battery cell. As you see here in this picture, the idea is that you can actually put it in an invasive way, so it should not sort of disturb the reactions in the cell. In this project, they go for rather large cells, 1 amp hour up to 5 amp hour cells, and try also to put a perspective of BMS onto this. How do you control all these sensors when you build them together, all these cells? And have a kind of estimation algorithm based on the sensoring data. So just like in the Instabat project, it's a lot of hands-on work, but it's also a lot of modeling and develop a new algorithm in this. But with a slight, it's not the optical fibers that are in the center here, there are other sensing technologies. And of course, in this case, there is also a cost-benefit analysis and recycling study, because if we want to add some smart functionalities into something, we need, of course, ensure it's not adding too much of extra cost, or that you can regain that cost in some other step of the usage cycle. And it should also be possible to recycle in a simple way. Next slide, please. So here, the level 1 in this 3-year project is to work on sensor for internal temperature and pressure. So they are integrated in a double matrix layout, as is described in this figure here, and with also added functionalities that can read out the sensor measurements. And here you have both the temperature sensors and the pressure sensors, and they are different. So you have 3 times 4 sensor matrix in this cell. And of course, that's why it's important to work with this 1 amp per pouch cells. You can't go really smaller. And when you go for larger cells, you can incorporate a lot more of sensors than you can at 1 amp per hour. Next slide, please. So this is an example of some results that you actually have now a temperature sensor, and it's a crimped temperature sensor array based on nickel aluminum alloys and made into a temperature sensitive structure. And it's possible to have a resistance temperature detector linked to this. And you see that they have now reached the early results where you can have measurements of this crimped sensor between -20 to 110. And there's a high linear behavior maintained also at negative temperatures. Next slide, please. Here. So that is the temperature sensor. Here's the pressure sensor. And here you have a capacitive pressure sensor. And the early results show that you can have a capacitance measurements of sensor under pressure. And you have above 1 kilopascal, you have a linear regime. And then now the group is working on evaluation and exploitation of different materials and device architectures, and further material optimization for this. And I should say that Matanuco comes from Ikelan in Bilbao in Spain, and working rather applied on what we, at the same time as working at very low TRL levels. And I think that's the beauty of the projects we have on sensors, that you can start with really novel things and very quickly move up to something where you're testing it at a rather applied level. Next slide, please. Yeah, the next thing, the level 2 sensors, they are reference electrodes. And these reference electrodes are printed on the separators in the batteries, and using different conducting materials like graphene, but also some electrochemically active materials. And in this way, the group hopes that they can do in situ electrochemical impedance spectroscopy, learn more on what's going on in the cell, and also probe if they have any hotspot or unwanted reactions. And they will also looking at using in operando measurements of electrolyte conductivity with these sensors. So now they are improving the location and shape and morphology of the sensors in the separators, and have done their early impedance spectroscopy measurements that you can see here, some results. Next slide, please. So the objectives of having now at least the embryo of a number of sensing technologies have met, but next thing is to really do the incorporation of these into the larger cells and take the cells to packs and control them with the modeling and the BMS. Next slide, please. Yeah, thank you very much. Here are the details for Matanuco and the Ikelan group, and you can find more on LinkedIn on this, but you can also find it here in the Battery 2030 Plus Expo for the Battery Innovation Days, and I think it has been put up in the chat more about this. I think we have a very good question in the chat that I would like to wait a little bit with. But before I move on to the Spartacus project, I would like to know if Olivier or Maitane, if you have any more comments on this one, on this presentation, on and what you know that work more on sensors than I do myself.
Not at this stage from my side. I think it's a good progress. There are also interesting sensors that are embedded in Sensibat. Also in the next steps and ongoing work on the battery management system and testing at module level. I think it's a very nice overview of what is going to be achieved in the project.
Thank you. Olivier, did you have any additional comments, please?
No, in my side, I'm also very happy for this overview and to show the progress in each project. And I think the difficulties of sensors preparation, integration, and so on are step by step. We find the way to go to the integration of sensor, and it's a good results.
Thank you. Thank you very much. Then I will move on with Spartacus, and the one that really are the organization that is behind the Spartacus project you see here. It's Sidetech, Arkema, it's VUB with Maitane, so I'm very grateful that Maitane is here, can help me with this too. And it's Fraunhofer with Gerhard Domann who is the coordinator of this project, and it was Henning Lorman who was supposed to give it. So if there is anyone in the audience that could add a little bit of comments in the chat later after mine, and hopefully supported by my Tane presentation, you are welcome to add your extra bit. But the Spartacus approach is slightly different from the previous two because it spatially resolves acoustic, mechanical, and ultrasonic sensing for smart batteries. It's very beautiful that the three projects have different approaches and they are all complementary to each other. And this, in this project, you don't have the sensoring directly embedded into the battery chemistry within the battery cell. You have it like a sensor array on the outside. And what you want to do is to measure locally changes in shape, Young's modulus, structure integrity, and thermal hotspots. And the use is sensor data and sensitive impedance spectroscopy for also enhanced modeling. So as in the Sensibat project, you also in the Spartacus project think a lot about the BMS, the cell management system, etc. So the modeling part is very important. And that is actually the skeleton of the whole Battery 2030 Plus project, that we have all these modeling tools and data collection issues that we share among all the projects. And that's a common sort of work we are doing to handle that and sharing that data. So here it's actually to build up a cell management system for this work and enable faster charging without degradation effects and safety issues. I don't know, Tane, do you want to comment on this slide? Something important?
I would like to comment that this cell management system is actually quite novel, and it will be an intermediate stage between the sensors and the battery management system, advanced battery management system, in order to make it a little bit smoother, the understanding and the development of the battery management system.
Thank you. Next slide, please. So here we see some of the sensing capabilities in this project. We have the ultrasonic sensing with piezo polymer sensors and doing power spectra analysis during cycling. You have ultrasonic sensing with piezoceramic sensors instead of polymers, where you can make an analysis of transmissive signals. And you see here 2 examples how a signal can look when it's state of charge 30 compared to state of charge 100. And then you have the stress strain sensing with the electric elastomer sensors, where you have measurement of deformation during cycling. Comments, Tane?
Yes, I would like to comment here. Here, of course, we see the status of the different sensors that we are targeting. Spartacus project. What we are going to receive now at VUB, because we are also a partner in the project, is the cells with the sensors integrated. And what we are going to do is we are going to test these cells in a special way, because we have developed a special dedicated testing matrix in which we are correlating the phenomena from the performance of the battery with the sensors, so that we can correlate very well what's going on in the cell to have a better understanding of the sensor, to have better, safer, and enabling fast charge, because of course we are going to target fast charge, and we are going to test fast charge in this project.
Thank you very much, Tane. I think this was the last slide for Spartacus. Yes. So thank you, Matan Luko. I know you are not listening, but thank you for put this together. And also Henning and Olivier. So Maitan and Olivier, we have one question in the chat. I think it would be nice if you had some comments on. Is there any specific sensor or measured phenomena that can make a difference in order to push the BMS evolution? What is your comment on that?
Yes, it's a good question, and thank you for still asking about the question of what is the way to improve the BMS function and the evolution. If you remember the presentation from Alexi, the BMS function need to have more information of what's happened inside the cells because when we use only the current and potential of the cells, you have many information are not visible. For example, the degradation and so on. You just show the effect of the degradation, not the degradation itself. And the idea about the sensor inside the cells or around the cell to show a better view, like a Spartacus, of what's happened inside the cell, it is to identify the phenomena when the phenomena appears. And by this way, by interfaces this information to the BMS, we can protect the cells to don't go far to the degradation way, and it's what we want to do with the sensors.
From my side, if I can complement.
Yes, please.
Yeah, I totally agree with the point of view of Olivier, and I think in order to push the VMS evolution, of course, is how you treat the data, how you develop this state of X estimation algorithms by using more and more, let's say, machine learning, artificial intelligence algorithms, and be selective with which state of X do you want to apply and with which techniques. And that, I think, it also helps together with the sensor implementation.
Thank you so much. As the slide shows, we should move on, that we have not only sensors, but also self-healing for improving battery cell functionalities. And I'm very grateful to have our two coordinators for Bat Forever, Maitane Brecher, professor and team leader at VUB in Brussels, and Maria Wilkman, senior scientist at VTT in Finland, for the Hidden Project, to give a short introductions, and then we can have more discussions, and I will bring up more of the questions coming up in the chat. So please, Maitane.
Thank you, Christina. Thank you very much for this introduction. Yes, my name is Maitane Berecibar, and I am a professor and team leader of the Battery Innovation Center at the Vrije Universiteit Brussels in VUB. And the presentation of today is called Self-Healing Battery Compounds to Survive Forever, which is presenting the Bat Forever project. Next slide, please. The aim of the project, so we want to develop self-healing battery materials and, of course, their advanced characterization and atomistic modeling. We are focusing on the self-healing mechanisms, which are related to two main prevention. First prevention is on the micro damages at the anodes and cathodes. And the second is to prevent the loss of material that the cathode surfaces suffer when charging and discharging several times. Here as well, what we are focusing on Bat Forever is in developing the prototypes, so assembling and manufacturing these self-healing batteries. And at the end, of course, one step further, we want to test the performance in real time, supported by simulation of the prototypes that we have developed. Additionally, here, I want to say that we are also targeting sustainability and sustainable actions in this project. Next slide, please. We can see the consortium of this key project, key partners from Turkey, Enver and Vestel. From Italy, we have FAM and Unimor. from Spain, Universidad Complutense of Madrid, from Luxembourg, CleanCarb, then we, the coordinators, VUB, we are from Belgium, and finally from Germany, 3 partners, Martin Luther University, DLR, and IOLITEC. Next slide, please. Here, the 5 main objectives. You can see some related images for objectives 1 and 2. They are, of course, coming together. Objective 1 is on the development of the innovative nanostructured anode and cathode particles and electrolyte to develop these self-healing materials. Objective 2 is together with this, the development of the ionogels for the generation of these self-healing battery components. And with all this, we go to the next objective, next step, advanced characterization, modeling, and simulation to define these self-healing influences and materials that we've done in the previous objectives. Next, as we can see in figure 4, we have some prototypes. So we want to develop these assembly and manufacturing techniques to develop tailor-made battery cells with self-healing properties. And finally, number 5 is the validation and the testing of these lithium-ion batteries with the self-healing properties. At this case, it will be tested in this scenario of a mobile phone. Next slide, please. Yes, we are already a bit more than 1 year in BAT4EVER, so we have some success stories. We can say that at the first 2 objectives, the NMC cathode particles are already synthesized. So this self-healing functionality is now under development, as well as the self-healing polymer based on this silicon anode, together with the ionic liquid embedded in this self-healing ionogel electrolyte. If we go to what's going on with this analysis of the materials, we are already in the structure or microstructure, composition, and morphology. We have analyzed already the NMC cathode particles, and we are already at the stage of the atomistic and macro scale modeling of the anode and cathode under the lithiation stage. We can go to the next slide, please. Yes, on the development of the manufacturing techniques, we have developed a benchmarking purpose in order to fit our assembly to the self-healing properties, of course, in which we have already listed the different key related parameters in order to develop this assembly in a suitable way. So all these activities that have already done will be then transferred this chemistry-specific know-how to the self-healing properties that we will develop at VUB in this case. And additionally, in this sustainable mindset, we are as well developing life cycle assessment studies in which we are accounting with 3 different tested scenarios. Next slide, please. Please, of course, follow us. Fantastic that we have today this event, but we have as well a webpage, BAT4EVER.eu, and a LinkedIn page as well under company BAT4EVER. Please, we will welcome you in our 2 platforms. And my last slide for thanking the partners of BAT4EVER for the excellent work, thanking as well the Innovation Days for inviting us, thanking the moderator, Christina, and thanks for all of you to being here listening to the presentation.
Thank you, Maitane. Thank you so much. I think we move on directly to Maria and the Hidden Project. Please, Maria.
Okay, so hello also from my side. My name is Maria Wilkman and I come from BTT Finland. And today I will also talk about self-healing and how to increase the lifetime of batteries by these methods. And the next slide, please. So I would like to just quickly in the beginning to introduce some different self-healing mechanisms that are available at the moment. And as already briefly mentioned in the first presentation, there are different types of mechanisms which can be divided, for example, into extrinsic and intrinsic healing. So extrinsic means that we are adding some additional healing elements into the batteries. For example, they can be inside microcapsules. Or intrinsic means that healing agents are directly integrated into the cell. They can be a binder or the separator or something else, but we are not adding anything extra to the cells. And on the other hand, the mechanisms can be divided into on-demand and autonomous self-healing. If we are using on-demand, we need to first sense the cell so we know when to trigger the self-healing, for example, by temperature or pressure or something else. Or then the autonomous systems can work by themselves, either do internal triggering. If there's a crack, then we get self-healing, or then there's a continuous operation without any triggering at all needed. And then finally, we can also divide them into 3 categories, like if they are single time healing, for example, the microcapsules, or then multiple healing. If we have capillary channels containing some self-healing elements instead of the microcapsules, we can use those like a few times to heal the battery. And then in the end, we can have a continuous or even infinite healing, where we could have, for example, reversible dynamic bonds, non-covalent or covalent ones. Or then we can, for example, have some additives in the electrolyte which continuously will help to heal the battery. And I have listed also here some really nice recent reviews if you want to have a look in more detail. Okay, the next one. And the main topic today is the hidden project. So the project is called Hindering Dendrite Growth in Lithium Metal Batteries. So we selected to focus, thank you, on this type of batteries. And here you can see a simplified view on our approach and our partners. So VDD is the coordinator, and then we have really nice consortium with 7 partners, so CNRS, CSCM, Berner Fachhochschule, Belenos, Specific Polymers, and Talos working together in this project. And we are developing mainly 2 different types of self-healing elements. So one is a self-healing electrolyte, which is made from liquid crystals. And the other one is a piezoelectric separator. And then we will use multi-scale modeling to design the electrolytes in order to get high enough conductivity and efficient dendrite prevention. The next one. Okay, yes, thank you. So this is regarding the liquid crystalline electrolytes. So this is an intrinsic on-demand method which we can use multiple times. And the idea is that if we just have a liquid crystal electrolyte, it can as such already prevent the dendrites from growing, since the lithium ions cannot freely move in the electrolyte layer, since there's a dynamic self-organized structure in the electrolyte. So they will guide the lithiums to land smoothly on the anode without having the dendrites. But we are then taking this also one step further. So if we heat the liquid crystal above the order-disorder transition, we hope to be able to even improve the self-healing reaction by refreshing the interface between the anode and the electrolyte. So this will be now tested, and then we will use modeling to design the best possible electrolytes we can make. And the next one. And here is the second method we are using, so the piezoelectric separator. This is an intrinsic autonomous and continuous method, so we don't need any triggering for this one. And the idea is so that since the separator is piezoelectric, when it's bended, we create the local electric field, like autonomously in the right position in the cell. So if the dendrite is growing, there will be a local electric field which will then guide the lithium ions again land smoothly on the anode. So this should help also to prevent the dendrites of growing. And we are in this project developing the processing, bowling, and the optimal composition for the separator materials. And next one. So as a conclusion, self-healing can be used to enable many things in the cells. So longer lifetime, which also helps to have better material sufficiency for the batteries, which is really important. We can increase the safety. What we could also get is new form factors, such as flexibility or even stretchability. So my background is in flexible and stretchable electronics, so there would be a high need for self-healing batteries as well. We can increase the energy density if we are able to then take, for example, lithium metal batteries in the better use, and even allow fast charging. And what is important, and which is really great in the Battery 2030 Plus initiative, that we need to collaborate with the sensing people, but also with the artificial intelligence and manufacturing know-how is needed. And then we should ensure that the recycling is still possible if we add new elements into the cells. Okay, and then the last slide. Okay, you can skip these. These were for the, if you can go to the last one. Yes, thank you. So last one is the thank you slide, and you can find also our LinkedIn page and the Twitter account where we will share more information about the project.
Thank you. But it's nice to see that you actually have some results already after the first year. That looks promising. And now we have a little bit time for discussions. I asked Maitane and Olivier to put on the camera so that we can see you. And also, I hope the audience will send in questions. Olivier, can you also put on your... Yeah, you are. And my first question to all of you is like the next step, if you look at the Battery 2030 Plus roadmap, that is to integrate self-healing and sensors together. Do you think we will be able to manage to do that 2 to 3 years from today, looking at your progress and where you are and the knowledge of the field? I think I start with a self-healing perspective. Are we mature enough in our knowledge about how self-healing molecules break, find each other again, or tick out as a medicine in the battery? What is your perspective on this? Should we start with Maria? Any comments on this?
I can start. So when I'm thinking about our project, the simple methods we could immediately take into use is temperature sensing, since if we need to trigger the self-healing mechanism by heating the liquid crystal above a certain temperature, we would need to know the accurate temperature inside the cell. So this is one immediate kind of benefit and relatively easy to take into use. That would be one example.
And how about you, Maitane? You have a very different approach to self-healing than Maria has.
Yes, we have a different approach. However, it should be feasible. For example, in our case, in Bad Forever, we use silicon. So, of course, pressure is something that we need to measure, and its pressure sensors is something that is tackled in the sensor projects. Also, in Spartacus. So I think it should be and it must be a match to have an understanding of the pressure, for example, when using silicon in batteries.
And you, Olivier, first of all, if I include in your question also, how difficult is it to put in the sensors without having short circuit of the cell? and then you add smart self-healing into that. How would you answer then?
Yes, of course. To input the sensor into the cell, we need to manage the short circuit or degradation due to the sensor himself. And the idea is to use, for example, for optical fiber, no electrical material on the optical fiber. It's the way to limit the short circuit. But of course, the integration of sensor is a challenging aspect of this work. But okay. Regarding to the self-healing, I think the sensor actually is able to give a view of the internal temperature of the cells, and by this way you can control or manage the temperatures and activate your self-healing function by this way. And for the pressure, we have also some pressure sensors. It's developed on the Instabat, on the Sensibat also, and it's yes. If it's two factors that you need to activate the self-healing, we can try to go to the test with this kind of sensors.
Thank you, all of you. I'm sorry that I interrupt your very interesting answer, but we have to end this. And I'm so grateful for all your support and the great achievements so far. And I hope to see you soon in the next sessions. Bye bye.
Okay, thank you.
Yeah.
Bye.
Thanks.
Bye.
Bye bye.
Bye bye.